Okay, so then we're going to talk about metabolism and nutrition. Now, this is where, like, in terms of like your book, so metabolism is actually pretty, like, at least the Martini version, it's almost like a biochemistry light part. And same, I think OpenStax is kind of like that as well. Do I expect you to know everything in the metabolism chapter? Not really. I just want you to know the basics. Because why? We did the digestive system, and now we have everything absorbed in our. So we have things absorbed in our by our cells lining our intestines and our small and large intestines. Now we have the nutrients in our bloodstream. How are our cells going to use those nutrients? So again, the main function of the digestive system is to absorb nutrients, and then you have what happens to nutrients? They end up in your bloodstream, and then now you need metabolism to kick in. So we're talking about what happens, the digestion on the cellular level versus digestion via the GI tract. So what are the main functions of metabolism? So the thing is that metabolism is how we get energy. This is how we fuel all the energy or all the chemical reactions our body needs to keep ourselves alive and maintain our cells and maintain homeostasis. That all requires energy from somewhere. So this is how we take our food and convert it to a form that our cells can use to maintain those chemical reactions. So energy is basically fuel for your body, but the thing is that this energy, what if you have too much of these nutrients, or say you want to store this energy for later, say if you're like about to do exercise or run a marathon, you want to store it for later. But also the thing is that during our daily lives, we also encounter like stresses, and we shed cells all the time, and we also cause damage to our body, and we have to replace lost cells and tissues as well. So metabolism is also important in taking the nutrients we get from our digestive system and also using it to repair the tissues and cells of our body. So repair, not just the energy, but also repair and maintenance. So it's fuel and maintenance. Are they signs in your feces that someone have diverticula? Ooh, that's something I would love to talk about, but we don't have time. Diverticulitis, yeah, that's a very interesting. Yeah, it's like basically these outpouchings of the intestines. But yeah, that's something. Maybe that's a good pack-back question. Okay, so when you think metabolism, what do you think of this? Like, if you ask anybody on the street, they'll ask what metabolism is. They'll probably say like, "Oh yeah, it's like saying someone has a fast metabolism or a slow metabolism." And somatotropes are, don't worry about that because that's kind of controversial right there. But a lot of people confuse metabolism with basal metabolic rate. So what is basal metabolic rate, or BMR? It's basically just how fast you consume, how much energy you consume per unit of time. So if it's like how much energy and it's basal because it's just like your bare minimum and your starting point. So this is when your body's at rest. Like say you just lied and didn't move at all, you didn't get up and do anything all day, and you just like stayed in bed and then you just exist or something. This is the energy you would need. Your basal metabolic rate for that day would be however many calories and energy you needed to keep yourself alive and keep yourself functioning during that day. But again, we're getting up, and if you exercise, your metabolic rate is going to go up because you need more energy. But yeah, the basal metabolic rate is that bare minimum of energy per time. So this is what some people often say is metabolism, and they say, "Oh, I have a fast metabolism, I have high metabolism, I have low metabolism." They're usually referring to metabolic rate. But physiology, so yeah, don't worry about this part right here. I'm not even going to talk about what these body types here because they're pretty controversial, and I think but they're still using it today. Like I think even like in so I checked on PubMed, and it seems to be like a lot of like, not throwing shade at like kinesiology, but it seems like a lot of sports journals tend to use those body type stuff still. But yeah, they're problematic. Okay, but what is metabolism in the scientific biochemistry and physiology term? So basically, metabolism is the sum of all the chemical reactions in your body, whether they're anabolic or catabolic, all the chemistry that's occurring in your body, all the chemicals, all the molecules, all the enzymes. That is metabolism, and that's what you need to keep yourself alive and maintain your cells and tissues, repair your cells and tissues, and provide all the energy to the cells and tissues. So you probably know some of these chemical reactions already, and hopefully these look familiar. How about this? Yeah, carbon dioxide in water makes carbonic acid and then dissociates into bicarbonate and protons, right? Or how about this one, especially if you've taken like cell biology, and I mentioned this one a few times in our course as well. So the cellular respiration or aerobic respiration equation. These are chemical reactions. So what about metabolic pathways? What do I mean by that? Well, okay, metabolism is chemical reactions, but what's a pathway? So let's take our famous like bicarbonate buffer system over here, and say let's represent each of these chemical compounds as a dot. Or if you know computer science or data theory, then you might let's say that they're points, and then we're making a tree here. So here what we have are nodes. Yeah, here we have nodes and these little points right here. So each point is a chemical. And this part right here I'm representing as these arrows, because why am I doing a double arrow? Because again, carbon dioxide and water can make carbonic acid, but you can also break it apart. It's a reversible reaction. That's what I'm getting at here. But remember that we have this other part of this equation. So I can represent this whole series of equations as this. So this graphical way of doing that. This is one way to represent a metabolic pathway. Each node, each dot is a chemical compound, and each connection and arrows between these dots is some sort of chemical reaction. Now, if we took all the possible metabolic pathways in your body, this is it. So every single dot here is some chemical compound. Every single line is some sort of reaction in your body. And this is going on in your body right now. So metabolism is very complex. Do I want you to memorize this graph? No, it's not April Fool's Day. I don't expect you to memorize this graph, but I want you to appreciate that metabolism is potentially complex, but I'm not going to ask you to know all that. What I want you to know is, okay, we know how to break down our food into basic molecules, but how do we convert those molecules into usable energy, and how can we use these molecules to repair our body? That's what I want you to get from this chapter over here. Now, first we have to talk about, okay, so we have food, and then we have these basic macromolecules, our carbohydrates, triglycerides, and proteins, and then we can break them down into smaller molecules via our chemical digestion. But now how do you actually get that and convert all of that into energy and building up your body? Well, what about this? So say you're into exercise and you want to build up and you want to bulk up. Do you want to do anabolism or catabolism? So let's ask, not cannibalism, but catabolic. So do you want anabolic reactions or do you want catabolic reactions if you want to build a lot of muscle in your body? And let's ask the chat. So yeah, you want to get like these people right here. What type of chemical reactions do you want occurring in your body? Anabolic reactions or catabolic? Yeah, you probably want anabolic reactions, right? Because, and I'm not saying like what we're talking about anabolic drugs here, but what is anabolism? You want to build up things, right? So when you have anabolic reactions, you're building something up and building bigger molecules. So when you want building up a protein, you want to take smaller amino acids and have a bunch of anabolic reactions that make a big polypeptide that makes up a protein. So this is where anabolism is all about building up. So when you have something like anabolic steroids, I'm not saying anyone's using anabolic steroids here, but anabolic steroids are supposed to build up new tissues by taking smaller molecules and building larger structures. So where to get those building blocks? This is why you need nutrients for anabolism, so because you're going to build up new things. So, but the thing is do you just get like super anabolic just by doing nothing and without any energy? No, this is why also when you build up new molecules, you also need to put in energy to put these smaller molecules together. So when you construct or build anything, that requires energy. Even if it's something simple, like you're just like gluing two sticks together, you gotta do all the energy to actually do all the movements to put these structures together. So all anabolic reactions, they require some sort of energy input. And proteins, again, these are, if you have anabolism proteins, this is why you need nutrition and you need energy to build up proteins and build up muscle tissue in your body. Now, catabolic, so catabolic is the polar opposite. So here's a cat, and what are they doing? They're causing, it's like, so here's all these cats, and especially that one up there is taking a larger structure and breaking it down into its parts. Or here we have like a cat taking a large structure and breaking it down as well. So catabolism is all about breaking down of larger structures and breaking it down into smaller parts. Yeah, I know that's not a cat, but sometimes they act like cats in like bird bodies. But what we have here is like catabolism is all about the breakdown and decomposition of things. So, what we should have there is actually, let me fix that slide real quick. Yeah, catabolism. So what you have with catabolism is you're breaking down larger molecules into smaller parts, and it requires little or no energy input. So again, compared to anabolic reactions, sometimes catabolic reactions, they're not spontaneous, meaning that they don't happen just by themselves. You might need a little push, just like that cat was pushing that big stack of cans over the edge. But once you get that reaction going, then the rest of it actually releases energy. So this is another big thing. Anabolism takes energy, so it stores energy. Catabolism releases energy. So if you want to take a nutrient and break it down into energy, you want to do catabolic reactions because they release energy. So energetics, it sounds kind of like redundant, but energetics is the flow and conversion of energy into different forms as well. So most physiological processes, again, if we didn't need energy, we wouldn't need to eat. Things would just happen by itself. So to keep yourself alive, you need energy to supply all the chemical reactions that take energy and keep yourself alive and repair all the cells and enzyme and maintain all the chemical reactions you need to keep alive. So one major substrate or chemical or molecule that's needed for this is ATP, or adenosine triphosphate. So why is it so important for our bodies? Well, it's easy to make ATP in our bodies, or relatively easy, because your bodies can store energy in ATP, but you can also, when you catabolize ATP and make ADP, that releases a lot of energy as well. So it's easy to store and release energy from ATP. But the thing about ATP itself is that it's unstable. So if you just have ATP floating around in a solution in a jar, it's going to spontaneously decompose by itself. So it's not a very stable compound due to the high energy in its bonds. So I like to think of it this way. ATP is like cash, like almost, or now I have to say it, assuming your country still uses cash, and now we're going more electronic. But it's like having dollars, or just like, or PayPal or Venmo or whatever is easy to use. ATP is the easiest way for your cells to store energy and also use up energy. But is it the only form of energy? Like, is cash the only form of is that the only form of currency? No, you can have other things. You can have other things that have value. You can have things like gold bars if you're very rich or something. There's other things that have value, just like how other substances have energy. But can you just go to an ABC store or 7-Eleven and pay in gold chains? Probably not, right? So not all of forms of energy are easily usable by cells, just like not all forms of currency are not easily exchangeable in everyday life. Yeah, so I think of it this way. All of these are currencies, but which is the most easiest to use in general? Which can you go to the convenience store and buy a spam musubi with? Probably the most easily the most easily used form. Okay, so what we have is we're building this up. So we're building up this electronic here, and now we have a final product. So do you think this is anabolic or catabolic? If we're doing this as an analogy, this process of taking something in its individual parts and building something bigger that's functional, do you think this would be an anabolic process or a catabolic process? And when I was in high school, my biology teacher made me memorize what catabolism was by putting the mental image of chopping up a cat in your... Oh, that's animal cruelty. I like my analogy better. Yeah, so it's probably yeah. So this is an example of an anabolic. What anabolic reactions are like. So when you're taking something in its basic components and building something bigger and complex, that is an overall anabolic process. Now, catabolic. What would be the catabolic process in this? Well, catabolism would be taking this whole bigger, larger structure and breaking it apart into smaller parts. Now, which requires more input? Well, which can you do for more energy? Which requires more energy? Anabolism or catabolism? Well, again, you need this part you can do for free. You can take some electronic and just throw it on the ground, and then you can end up with that for no, yeah, it doesn't cost you anything to break your phone. But to build a new phone, that takes a lot of energy. You gotta supply the living wages of all of this. You gotta buy all the parts. You gotta supply all the electronics. You gotta supply all the machines and robots. So which costs more money? Well, this part right here. And why do I use this analogy and between money and energy? Well, anabolic processes, they require a lot of energy input. So that's what I'm getting at here. Just like it takes a lot of money to build up this part right here and very little money to do this process right here, anabolic reactions require a lot of energy input. Okay, so then let's talk about our macromolecules. And yeah, but what we have here is looking, macromolecules are carbohydrates, fats, lipids, proteins, and nucleic acids are negligible because they don't really contribute to our energy content. Because yeah, in rare instances you can get energy from them, but that's more for starvation. And there's also ethyl alcohol or ethanol or drinking alcohol, like things like vodka, that, or you get beer or wine. This would be ethyl alcohol, and that does have calories, and this is why you like even alcoholic drinks, even if they contain minimal carbohydrates, they're still going to have some sort of caloric content. And this is why there's no such thing as a diet alcoholic drink, because alcohol has calories. And these values are what I want you to use for PHYL 142. Again, there are other values in other classes, but use their values. But why did I order it in this fashion right here? Well, your body likes to use carbohydrates first, and then as it goes from carbohydrates to fats, lipids, and then proteins. Because again, you don't want to break down your skeletal muscle. You don't want to break down that big muscle called your heart in the middle of your chest. So your body's going to try to preserve proteins as much as possible. But if you burn through all your carbs, if you burn through all your fat, then eventually you need energy from somewhere. So carbs are the most easily used form of, or nutrients, or the nutrients that are most easily converted to energy. Fats are, I wish it was the other way around, because like losing fat is harder than burning carbs. This is why we have to fats are a great storage form and they have a lot of energy, but your body likes to burn through the carbs first before they burn through the fat. But once you burn through all the fat, then if you're not having enough nutrition, then you're going to have to burn through your proteins. And nucleic acid, this is why it's like you have to be like really starving to use nucleic acids for. So don't worry about for this class. Now we probably don't have time to talk about carbohydrates, so this is the first steps right here. And so what I wanted you to get from this is like, okay, define metabolism, define anabolism, catabolism. We'll probably have to cover how we convert the macromolecules to energy for the next, yeah, it's already like 2:20. Let's save it for the next lecture, right? So then next lecture we're just going to try to burn through burn through the nutrients, pun not intended. We're going to go do that next week so enjoy your 3-day weekend, because like again, Friday it's interesting, like they don't give Easter off, but it's like Good Friday is a state holiday. It's not a federal holiday. But yeah, it's a non-instructional day, so if you're logging on Friday, I'm not going to be here because check the course calendar and check the school calendar. It is a non-instructional day. So enjoy your long weekend and see you then. Stay healthy and stay safe until then, all right? So see you on Friday.